Mirrors are not only used for aesthetic reasons, but also for security purposes. For example, the concept of reflection is used when checking visitors at the gate at an appropriate angle. It also saves lives when driving, as the rear and side mirrors are used when moving to a different lane safely. Lenses, on the other hand, are very important for people who have difficulty reading, as they use reading glasses for better comprehension. While looking in a plain mirror, we see our reflection looking back at us. As you look towards your reflection, have you ever wondered how these reflections are made? In this chapter, we will deal not only with mirrors and reflections, but also with lenses. Now, we will be talking about luminous versus illuminated. In the presence of light, humans are able to see their environment using their eyes. The light emitted from an object is transformed into signals which are brought to the brain. Afterward, these signals are interpreted by the brain to determine the information about the object being looked at, like the shape, color, and even the movement of that object. Generally, these objects can be categorized into two: luminous and illuminated. Luminous objects are objects which can produce their own light, while illuminated objects don't produce their own light but instead reflect light rays from other light sources. Most well-known luminous object is the sun. Because of the light rays produced by the sun, objects do not produce their own light but instead reflect light from other light sources. Since most of the objects that we see around us are illuminated objects, humans normally will not be able to see these objects in the dark. This is the reason why we have difficulty seeing things during the night. Hence, the amount of illumination is defined to be inversely proportional to the amount of light energy that radiates over the area. The unit of illumination is called lux. Its equation can be seen below. Let us proceed to its sample problem. The sample problem states that calculate the illumination of a flashlight at 5 meters away if it generates an illumination of lux a meter away. Using the equation, we can say that its illumination is 0.8 lux.
Formation of images in a plane mirror. Observe this diagram shown. Consider two persons viewing an object through a plane mirror from two different positions. By the law of reflection, light emitted from that object is reflected from the mirror and along the line of sight of the person viewing the object. By extending the line of sight of both persons further back from the mirror, there will be a point at which the two lines will intersect. This point of intersection is known as the image point. From this image point, we are also able to determine the location of the image in space from the perspective of the observer. The properties of this image may vary depending on the kind of mirror on which the image is produced. A handy tool that can be used to visually examine the mirror image is through the use of ray diagrams. Similar to free body diagrams, ray diagrams portray the path of light as it converges or diverges to form an image. Qualitatively, the image may be described as virtual or real and upright or inverted. A virtual image is produced when the light rays diverge or appears to converge from the mirror. Image appears to be formed in a position somewhere behind the mirror, while a real image is produced when the light rays converge to a certain point. Real images are always formed as the same side as that of the object. There are characteristics of images formed by a plane mirror. The first characteristic: the image is always virtual. The mirror image will always be virtual since the light rays will not converge toward one another. The next characteristic is the image is upright or laterally inverted. When we say laterally inverted, it is a phenomenon in which, while facing a plane mirror, if you raise your right hand, the image will look like it is raising its left hand and vice versa. While in upright, it implies that the image matches the vertical orientation of the object. Next characteristic is that the image size is as the same size of the object size. For example, if the height of the person is 5 feet, then the image's height will also be 5 feet. Characteristic is that the image formed is at the same distance from the mirror as the object is. Here we have a sample problem. Problem is, what is the image distance and the image height of a 5.6 meter tall object if it is placed 1 5.5 meters away from a plane mirror. In the case of a plane mirror, the image height and image distance are simply the same as the object height and object distance respectively. Therefore, h sub o equals h sub I is equal to 5.6 meters, and d sub o equals d sub I is equals to 1.5 meters. Hence, the image height is 5.6 meters, and the image distance is 1.5 meters.
Hi everyone, I am Shanine Kate Bibaran, and now let's proceed to curve mirror. We have described the image produced by a plane mirror, so now let us consider the mirror image for a curved mirror, specifically for a spherical mirror. So now, what is a spherical mirror? Spherical mirror can be imagined as a hollow sphere on which surface of the inner sphere is made up of a reflective material. So now let us consider this image. So we have an example here of a drawing diagram to further understand the spherical mirror. If a portion of the sphere were sliced both sides, then two curved mirror would be formed. So in the left side, we have the concave mirror, and the right side, we can form the convex mirror. And later on, I will furthermore discuss about the concave and the convex mirror. A concave mirror is a kind of spherical mirror wherein the curve where the reflective surface resides is inward or going to the right, while the convex mirror is when the curve of the reflective surface is outward going to the left. Ang mirror kay magdepende siya sa type of mirror nga gigamit niya. Magdepende pud sa object nga mag-reflect. Pero kanang ang component sa spherical mirror kay the same ra siya sa both cases. So, the components of a curved mirror consist of a principal axis, the center of curvature, I don't know how to pronounce that word, basta kana, then the focal point and the vertex. So, the principal axis is an imaginary line drawn along the center of the curved mirror. And next is the center of the curvature. This is the point along the principal axis which represents the center of the sphere. Next is the vertex. It is the point where the principal axis intersects with the mirror. Next is the focal point. It is simply in the midpoint between the center of curvature and the vertex. So, ang principal axis, kay kanang example, mautahay ni ang curve sa mirror. Ang kanang diri kay mauna ang kanang principal axis, ang kanang linya. Diri ang kanang focal point and diri ang center. Kuha na nila kay mao ang vertex. Anya naapod na. So now let's proceed to mirror equation. Consider an object with a certain height which is called as h sub o were placed at a position d sub o along the parallel axis in front of a concave mirror. So first, the ray moving parallel to the principal axis will reflect toward the focal point. Second, if an incident ray passes through the focal point, then the incident ray will be reflected back traveling to the principal axis. And this is the equation will be used. H sub o over h sub I and d sub o minus f, which is the focal point, over f. And kuan ani kanang naapa ni siya kanang mga angles nga imong ikuan before ka makakuha ni nga equation, imong i-take nya. Lisod naman to siya, so ilargo na lang nato siya sa equation. So mao ni ang equation. Concave mirror. Suppose a object is placed at a certain distance from a concave mirror. Before drawing the ray diagram, it is important to take note of the two rules which all concave mirror follows. First is an incident ray moving parallel to the principal axis will reflect toward the focal point. Second is an incident ray passes through the focal point, then the incident ray will be reflected back traveling parallel to the principal axis. So this is the example of a formation of a concave mirror. This is the front and the back. And ang pasabot ato sa mga rules if ang kaning ang mao ni ang rays niya. Ang first adto nga example kay sulti nga ang ma-travel parallel sa axis. Sabihan yan, ray ka maana sa like wala nagka-reflect tanan ba like mas straight ra ara. Tas ang second kay kuan kanang ma-reflected back sa parallel axis basta dira di na ta mo go deeper ana kay maura na basta mo na yung formation sa concave mirror. By illustrating ray diagram, we can generate an equation which can help determine the distance of the image relative to the distance of the image from the mirror. And that's all my report. Thank you.
Good day everyone, my name is Casey Jean Ilimbaga. So to better understand, let's proceed to the sample problem about the magnification. So here's the example. A 3 meters object is placed 8 meters away from a concave mirror. If the focal length is 5 meter, what is the magnification? Again, using the mirror equation, we have d sub I is equal to d sub O times F over d sub O minus F. So just simply substitute the given, which is the d sub O, the distance of object, which is the 8 meters, and the focal length is 5 meters, over d sub O, which is 8 meters, minus focal length 5 meters, and we get 13.33 meters. From equation 5.15, we find that the multiplication is m is equal to negative d sub I over d sub O. Since we already get the d sub I, so 13.33 meters over our d sub O, since our d sub O is 8 meters, 13.33 meters over 8 meters, and we get negative 1.67. So let's proceed to the image characterization for concave mirrors. So from the mirror equation, we find that the image is dependent on the position of the object along the principal axis. Thus, let us consider the following cases. So first is the situation 1. The object is beyond the center of curvature. So here, the image is real and inverted, and the image distance and the image height are both less than the object distance and the object height, respectively. So next is the situation 2. The object is the center of curvature. Here, the image will always be real and inverted in the care of concave mirror. The light rays converge to form an image that is real, inverted, the same as the object. This means that the object form is not magnified and appears in an inverted orientation compared to the object. So next is the situation 3, which the object is in between the center of curvature and the focal point. In here, the image height and the image distance become greater than the object height and the object distance, respectively. In this case, the image will be inverted, such as the object standing up will result in an upside down image. And also, the image will also be located at the center of curvature. So next, in the situation 4, in which the object is at the focal point. In here, there is no object is formed. In here, the light rays from the same point on the object will reflect off the mirror and will neither converge or diverge. After the reflection, the light rays will travel parallel to each other and will not result in the formation of an image. Though last is the situation 5. This is when the object is between the focal point and the vertex. So here, the image completely changes and the image becomes virtual and upright. It also becomes magnified, meaning that the dimensions of the image are greater than the object. And also, the image will always be located at the position opposite side or behind the mirror. You can locate the image behind the mirror. So that's all. Thank you.
Now, we will tackle about convex mirror. What is convex mirror di? A convex mirror is a type of mirror where the curve of the reflective surface is outward or going to the left. Example of this is kanang sa 7-Eleven gani nga mirror. I assume nga nakaadto naman ang tanan ng 7-Eleven sa. So naanay mirror ara nga usahay gani mao ang picturean sa mga teenagers. Other example pod is kanang spoon or kutsara nga permi nato gamiton. Ang sa part ana nga ara ibutang ang food is example na siya sa concave mirror. However, the back part sa spoon is convex mirror na siya, where the image is diminished and upright. Now, we will not go deeper sa example about ana, since we will focus sa pag-find sa reflection sa object, which is iyang image. We can apply the rules we use to illustrate the ray diagram of a concave mirror. Before nato pangitaon asang image, kay unahon nato pangitaon iyang image point, like the tip sa object. Figure 1 shows point A as the vertex, point B is the focal point, and point C is the center of curvature. The anatomy of a convex mirror is exactly like the concave mirror. Pero ang sa reflective part sa convex mirror is at the outward curve. The rules for concave mirrors are followed, where the incident ray is moving parallel to the principal axis, nya mo reflects sa point B, which is ang focal point, then the incident ray passes through the point B, nya that incident ray will be reflected back traveling parallel to the principal axis. Now that we have identified the image point, we will draw the image from the principal axis onto the image point. Shown in figure 2, the image is virtual small, upright, and the image is between point A and point B. The closer the object is to the mirror, the higher the image height will be, which shown in figure 3. After learning about convex mirrors and the ray diagrams of a convex mirrors, we will now proceed to the sample problem. So an object is placed 5 meters away from a convex mirror. If the focal length is 2 meters, what is the image distance and the magnification? So by analyzing the problem, kaya ang ipangita is the image distance, which is the d sub I, and the magnification. In convex and concave mirrors, the left side of the mirror is usually the front, and the other side would be the behind part. If the image is in front of the mirror, which is in the left side, DI is positive. So if the image is behind the mirror, DI is negative. Whenever DI is positive, it's a real image. And whenever DI is negative, you have a virtual image. For concave mirror, the focal length is positive. For a convex mirror, the focal length is negative. Now for the given, we have the object distance which is the d sub O, which is 5 meter, and the focal length is 2 meter. For the solution, the first thing that would come to our mind would be the mirror equation because it contains d sub I and the other variables that it has also satisfies the given. So since convex mirror atong topic, our focal length is negative since the focal length is located at the other side of the mirror. In the equation, negative 1 over f equals 1 over d sub O plus 1 over d sub I. dO is the distance between the object in the mirror. And di is the distance between the image in a mirror. That will become the equation of di is equals to negative d sub O f over f plus d sub O. So the dO is 5 meter and f is the 2 meter. Then after plugging, we can come up na sa answer, which is negative 1.43, which is negative 1.43 meter. That is the answer for the image distance. Since na-find naman nato ang image distance kay ato na pod sunod pangitaon iyang magnification. So using the equation m equals di over do, tapos plug in, which is atong di is negative 1.43 meter and ang do is 5 meter, tapos i-divide, then 0.29 is the answer for the magnification.
Light rays refract when moving from one place to another. Based on Snell's law, the angle at which the light ray refracted changes with the initial incident ray. This refraction can cause the rays to converge or appear to converge, forming an image. To observe this effect, the materials through which the light travels must be transparent. Such transparent materials that refract light to create images are called lenses. Lenses are categorized into two: converging and diverging. Now let's imagine two spherical lenses to understand converging and diverging lenses. If the two spherical lenses are intersecting, it's a converging lens. Converging lens is also known as the double convex lens. Double convex lens can be thought as the two convex mirrors facing at the opposite direction attached to one another, hence the name double convex. Now, if the two spherical lenses are separated, the space between them represents diverging lens. Diverging lens is also known as a double concave lens. Can be thought of as two concave mirrors facing at the opposite direction, attached to one another, hence the name double convex. Converging lenses are thick in the middle and thin in the edges, resembling a bulging shape. Diverging lenses are thin in the middle and thick in the edges, resembling a thinner shape. Despite the differences in shapes, both types of these lenses share similar internal structure. A lens consists of focal points P and C, at both sides of the lens, and the principal axis connecting the two mirrors. A lens has a vertical axis which splits the lens into two parts. Similar to curved mirrors, lenses have a center of curvature, though is referred to as twice the distance of the focal points A and D.
So let's talk about the diverging lens. Diverging lens follow the same idea of converging lens. To illustrate the ray diagram, for a diverging lens, one should follow the three rules. First, An incidence ray parallel to the principal axis will refract and extend a refracted ray to a focal point. So, step 1, we have to draw the three lights ray. First, parallel to the principal axis. Second, straight to the center of the lens. Third, passing through the focal point on the other side of the lens. Second rule, an incidence ray moving towards the focal point on the other side of the lens will refract directly to the focal point. Step 2, the lens ray parallel to the point axis. First, will retract and can be extended to the focal point P, while the light ray passing through the focal point on the other sides of the lens. Third, will be refracted directly the focal point C, after which the apparent rays will be refracted parallel to the principal axis. Third rule, an incidence ray passing through the center of the lens will simply travel to the same direction when it passes through the lens. And last step, an image is formed from the intersections between the three lights ray. The image formed at the position will be virtual and erect.
The computation of lenses involves using principles of geometric optics and formulas such as the lens equation and magnification. These equations describe the behavior of light rays as they pass through lenses and form images. The lens equations relates to the focal length 1 over f of the lens to the object distance dO and the image distance di, allowing for the calculation of the parameter given the other two. The magnification formula relates the heights of the object, HO, and the image height, HI, providing a measure of how much larger or smaller the image is compared to the object. By understanding and applying these formulas, one can construct word diagrams to visualize the formation of images and analyze their optical properties in various scenarios. Lens equation is 1 over f equals to 1 over image distance plus 1 over object distance. Magnification formula is magnification equals to image height over object height equals to image distance over object distance. Farsightedness, also known as hyperopia, is a common refractive error where nearby objects appear blurry, while distant objects can be seen more clearly. This condition occurs when the eyeball is too short or the cornea has insufficient curvature, causing light rays to focus behind the retina instead of directly on it. As a result, images from close objects are not sharply focused on the retina, leading to blurred vision when looking at near objects. Farsightedness can often be corrected with convex or converging lenses, which converge light rays before they enter the eye, compensating for the eye's inability to focus on close objects by refracting light to a point closer of the retina. Other treatment options may include refractive surgery or contact lenses for individuals seeking alternatives for corrective lenses. Corrective lenses are widely used to address vision problems and improve visual acuity. For individuals with nearsightedness or myopia, which is characterized by difficulty seeing distant objects clearly, concave lenses are commonly prescribed. These lenses help to diverge light rays before they reach the eye, allowing distant objects to come into focus on the retina. Conversely, for individuals with farsightedness, hyperopia, where nearby objects appear blurry, convex lenses are prescribed. Nearsightedness or myopia is a common refractive error where distant objects appear blurry, while close objects can be seen clearly. This condition occurs when the eyeball is too long or the cornea is too curved, causing light rays to focus in front of the retina instead of directly on it. As a result, images from distant objects are not sharply focused on the retina, leading to blurred vision. Myopia can be often corrected with concave or diverging lenses which cause light rays to diverge before entering the eye, allowing distant objects to come into focus of the retina. Other treatment options may include refractive surgery or orthokeratology or corneal reshaping for individuals seeking alternatives to corrective lenses.
So to summarize the all topics in chapter, first, luminous objects are objects which can produce their own light, while illuminated objects cannot. but instead reflect lights from other light sources. Second, the path of light is portrayed through a ray diagram. Third, virtual image is produced when the light rays diverge or appear to converge from the mirror, while a real image is produced when the light rays converge to a certain point. Fourth, a concave mirror is a kind of spherical mirror wherein the curve where the reflective surface resides inside, while in a convex mirror, the reflective side of the curved surface outside. And fifth, the components of a curved mirror consist of the principal axis, center of curvature, the focal point, and the vertex. And sixth, quantitative information about the image distance, the focal length, or the object distance can be obtained through the mirror equation, like this, where f is the focal length and d sub I is the image distance and d sub o is the object distance. And 7, the magnification is the ratio between the image and the length object dimensions. M is equals to h sub I over h sub o equals and minus d sub I over d sub o. Number 8. For a concave mirror, a real and inverted image will always be formed if the object is placed beyond the focal point. Number 9. For a convex mirror, a virtual and erect image will always be formed. And lastly, number 10. Lenses can be classified into two. First, converging lens. Second, diverging lens. Thank you.
Thank you for watching our video.